Don't know if anyone else is going to, so we can get started. So last week, well, let's really quick reestablish high-level intuition for what this chapter is about. This whole chapter is about constructing new topologies from existing topologies. In the first section, we talked about subspace topologies, how you can naturally induce a topology on a subset as long as it already existed in some topology. The standard way we were doing that is we were thinking about surfaces here in R3 and how we could easily construct a topology on them from thinking about how open balls would intersect with that surface. So that was subspace topologies. Then the second section, which we didn't quite finish, was on product topologies, where you have a topology on some set X and you have a topology on some set Y, and you use those topologies to construct a new topology. And pictorially, the way we think about that is the way it's drawn out here. Again, don't read too much into this picture. It is not the case that X is the real numbers or that Y is the real numbers. It's just a picture to help our intuition. So we think about X as a topological space. If A was an open set in X and Y is a topological space and B is an open set in Y, then we would think about the open set A cross B as that portion there, right? So this is how we were thinking about product topologies and cross products in general. We like to take this picture of them, have this picture in mind. With it, wanted to note a couple gotchas when we're working with cross products. A trap that's easy to fall into that this picture illustrates quite nicely. So let's imagine that we have these two topological spaces, X and Y, right? And A1 and A2 are open in X, and B1 and B2 are open in Y. And so I'm going to look at the set A1 cross B1, that one's there, and A2 cross B2, that one's there. Now notice, first of all, that if I do A1 intersect, let's all those up. If we do A1 intersect A2, that's a B1, and this is a B1. Okay, if I do A1 intersect A2, A1 intersect A2 gives me that little sliver right there. It's that interval. Here's A1. A1 exists just in X.
Right.
So A1 is that, A2 is that, A1 intersected with A2 is that little interval there. Similarly, B1, B2, B1 intersect with B2 there. Notice that if I look at A1 intersect A2, and I look at B1 intersect B2, and then take their cross products, I get this area that's shaded with both the blue and the purple.
Yep.
Similarly, if I would have started out with A1 cross B1, which is a whole blue square, and then looked at A2 cross B2, which is a whole purple square, I guess those are rectangles, not necessarily squares, and then look at their intersection, it gives me the exact same portion. So if we do the intersections, then we take the cross products. That's identical with first taking the cross products, then doing the intersection. However, notice that this is not the case with union. That's an easy trap to fall into. So notice that A1 union A2 gives me this whole interval. And B1 union B2 gives me this whole interval. And so if I were to do this whole interval cross with this whole interval, I would also get these orange portions up here. And the orange portion down here. That is very different than looking at A1 cross B1, union together with A2 cross B2. That leaves out the orange. So this one gets the orange, this one leaves out the orange. Very different things. Okay. So reminding us about product topologies and how we think about these cross-product things, there's a nice picture to help us. Now let's recap really quick the definition of exactly what cross-product topology was. We had 3 proofs to do, and then we'll move on to the quotient topology. So the definition of a cross-product topology. Remember, it's a topology we're defining on X cross Y using the topology that already exists on X and using the topology that already exists on Y. So we assume X and Y already have their topologies, and we're constructing a new topology using those. So in total, we're talking about 3 different topologies. The topology on X, the topology on Y, and then the cross-product topology that results. Okay, so let X be a topological space. So X has its topology. and Y be a topological space, so it has its topology. So those are two topological spaces. Then the product topology on X cross Y is generated from this basis. What is this basis? This basis is the cross product of two sets where the first set is open in X and the second set is open in Y. So pick an open set in X, pick an open set in Y, take their cross product. That's a basis element. So if A1 was open in X and B1 was open in Y, then A1 cross B1 is a basis element. Similarly, A2 cross B2 would be a basis element. Now notice that this is a basis. We're not saying these are all the open sets. We're saying that this is just the basis for constructing open sets. So it is not the case that every open set in the cross product topology can be represented as an open set crossed with an open set. If I take an open set and I cross it with an open set, I for sure get an open set. That's true, but the converse isn't true. If I start out with an open set in the cross product topology, it is not necessarily an open set crossed with an open set. And this right here is a perfect example. In our topology, we want blue union pink to be open. But notice I cannot get that by choosing something over here and crossing it with something over here. There's no way for me to get the blue and the pink without accidentally getting the orange if I try and do open set cross with an open set. Right. So this blue union together with this pink cannot be represented as an open set down here crossed with an open set up here. So that's why this is just a basis and not all the open sets. So these give you your basis elements, and then any union of these things is also open. So blue is open because it's a basis element, pink is open because it's a basis element, and now blue union pink is open because it's a union of basis elements. Any union of basis elements is still an open set. And so that gets us all the sets that we expect. Because naturally you would have expected, if I had just asked you without talking about any of this, is the blue union together with pink open? You naturally want to say yes, that should be open. So that's why this is just a basis and not all the actual open sets. Now we proved last time that we don't have to have this massive of a basis. It doesn't need to be the cross product of any two open sets from X and Y's topology. It turns out that we can define it to be the cross product of any two basis elements from a basis on X and a basis on Y. So we can be more restrictive. We don't have to use all their open sets. We can just take only the basis elements from X and the basis elements from Y and use our cross products. And that generated us a basis for the product topology. That was one of the major theorems from last time. Okay. So our first theorem that we're going to prove today is going to be Theorem 310. Notice that we do Theorem 310 then Theorem 39. That's just because this kind of jumps into it all so fast, I decided this was probably an easier one to ease us into. So that's why the numbering there. But let's prove this. Theorem 310. So let X cross Y together with tau be the product topology on X with tau sub X and Y with tau sub Y. So we have three different topologies that we're talking about. I have X together with tau sub X. Maybe draw it down here so I can write my proof above it. I have X together with tau sub X is one topology. And I'm taking the cross product of that with Y together with tau sub Y. And the resulting topology that it gives me is X cross Y, don't know why I keep doing lowercase y's, together with the topology that we gave it. So these are the three topologies that we're talking about. So this is the product topology. Oh, I just called it tau. Product topology, topology on X, topology on Y. Okay, and let A be some subset of X and B be some subset of Y. Not B be a subset of B. So A is a subset of this thing, B is a subset of this thing. Notice A cross B is going to be a subset of this thing. Okay, what are we trying to prove? We're trying to prove that the interior of A crossed with the interior of B is equal to the interior of A cross B. Now, notice that we're using two different symbols for interior. You're probably used to the circle above it for interior of the set. That's what we typically been using. Notice that there's no good way for me to write A cross B and put a circle above it. That's weird notation. So I just did int for interior there. But it means the same thing as circle. Just applying to the whole set. So I'm trying to prove that the interior of A cross the interior of B is equal to the interior of A cross B. Talk about 3 different topologies. The interior of A is an open set on X. The interior of B is an open set on Y. The interior of A cross B is an open set on this topology. So 3 topologies right there. Let's remind ourselves, what is the interior of a set? What's a high-level way we say it?
It's the largest open set.
The largest open set that you can contain inside of A. Or another way we say it is it's the union of all open subsets of A. Both of those perfectly valid ways to think about it. Okay, so instantly, always and forever, right out the door, I know that A interior is a subset of A. And B interior is a subset of B. And the interior of A cross B is a subset of A cross B. The interior of a set is always a subset of the whole set.
I forget what the circle interior means, that little circle on top.
That circle on top means we're talking about the interior of A. We're not talking about all of A. So imagine we're in the standard topology on R2. The plane.
Oh, yeah.
This right here, you know, is not an open set. Here's a potential A.
Right.
The interior of A would be this, excluding all the boundary points.
So you wouldn't want to call that just the open set of A?
Exactly what you had intuition for when you said the open set of A is what the interior of A means.
Okay.
Because notice that this, just taking this small portion right here, that's also an open set inside of A. There's an infinite number of open sets inside of A. This is the biggest one inside of A. You can't get any bigger and still have it be open.
Oh, okay. Interesting.
Okay, interior of A. Same thing with interior of B, same thing with interior of A cross B. Okay, so there's our intuition, reestablishing some intuition for what these things are. Let's actually do the proof. So I just wrote my 3 proofs here. We'll just reuse the same space over and over again. I don't know if this picture will help in any way, but all right, so let's do proof of theorem. We're doing proof of theorem 310. All right, 1. So we're proving this. So we have this topological space, this topological space, this topological space. I'm trying to prove that this is equal to this. How do I prove that 2 sets are equal?
You show that they're also the subsets of each other?
Exactly. I need to show that this is a subset of this, and then this is a subset of this. So 1. Observe that A interior is a subset of A and is open in X, comma, and B interior is a subset of B and is open in Y. Okay, so if A interior is open in X and B interior is open in Y, then A interior cross B interior is open in our product topology. What is our product topology? It's generated from a basis of cross products of open sets, where U is any open set in X and V is any open set in Y. Here is unopen set in X. Here is unopen set in Y. So A interior cross B interior is A open set in X cross Y. So 2. Then A interior cross B interior is open. And A interior cross B interior is a subset of A cross B. I know it's open in our product topology because it's a cross product of open sets. And I know that it's a subset of A cross B because that's a subset of that and that's a subset of that. So 3. Then, what do we know? This is an open subset of this set. What is the interior of A cross B? It's the union of all open subsets of A cross B. Here is unopen subset of A cross B. The interior of A cross B is the union of every open subset of A cross B. So then I know that A interior cross B interior must be a subset of the interior of A cross B. Has to be. Okay, so now let's go the other way. This time, I need to show that this is a subset of this. And since I have to break it up, this is probably going to be easier to pick a point out of here and show it's in here. So that's how I'm going to show that this is a subset of this, rather than doing it directly like this. I'm going to grab an arbitrary point out of here and show that that point is also in here. If every point in here is also in here, then this set is a subset of this set. So I'm going to grab an arbitrary point of here, show how you can show that point is in here. So any point you find in here, I'm going to show how you can prove it's also in here. Therefore, every point in here is in here. Okay, so let xy in the interior of A cross B. So I grab some random point in the interior of A cross B. I now need to show that it is in this thing. A's interior crosses B's interior. Okay, so I know that x cross y is in the interior of A cross B. The interior of A cross B is?
A interior cross A B here.
Well, we gotta prove that, but what do I know about this?
It's a subset of A cross B.
We know it's a subset of A cross B. Good. So I know that x is going to be in A, y is going to be in B. That's good. What else do I know about it?
It's an open set.
It's an open set in our product topology.
Yeah.
So if this is a point in our product, if this is a point in one of our open sets, and all our open sets are generated from a basis like this, then there must exist some u that's open in x and some v that's open in y, such that xy is in those. This is probably easier to write out than say it all in words. Okay, sorry. So what does that give me? That gives me that there must exist u in x's topology, comma, and there must exist v in y's topology, such that x is in v is a subset of A, and y, x is in u, is a subset of A, and y is in v is a subset of B. How do I know that? In general, if I have some random open set, and I know that there's a point in that open set, if that open set was generated from a basis, I know that there has to be some basis element containing that point. That's a subset of our initial set.
Yep.
Oops, where this is a subset of A interior and this is a subset of B interior. Because, well, we'll just leave it like this and go from there. This will be enough. Okay, so I know that there has to be some basis element containing that point, but our basis elements by definition are open sets in X crossed with open sets in Y. So, since it's in here, there has to be some basis element containing it, is basically what this says. There has to be an open set in X and an open set in Y, such that our point is in U cross V, or X is in U and Y is in V. And the sets can't go outside of the set. The basis element is contained entirely within it. So I know that U has to be a subset of that thing, and V has to be a subset of that thing. Okay. So 5. Then, let's see. X is inside an open set, and that open set is a subset of A. So X is in an open subset of A. So X is in?
A.
It's in A.
Open.
Here's an open subset of A. I know X is in it. So what must X be in?
Oh, interior.
A's interior.
Backwards.
So then X has to be in A's interior, because it's in an open subset of A.
Yeah.
And Y has to be in B's interior, which gives me that XY is in A's interior cross B's interior, which gives me that the interior of A cross B is a subset of A's interior cross B's interior. As Bradley showed, grab any random point out of here, it's also in here. Therefore, that's a subset of that. But we had, first we already showed, where did we show it? Right here. We showed that's a subset of that, and now we showed the other way. Therefore, 6, therefore the sets are equal. Therefore, the interior of A cross B is equal to the interior of A crossed with the interior of B. And we are done. Any questions on that proof?
Pretty easy.
Yeah, not a bad proof, pretty straightforward. Good one to dip our toes into. The only messy thing is you kind of have to remember what your three topologies are and exactly what it means to be in this topology. Going back to our basis here, our definition of the product topology.
Can you construct a product topology on any basis? Like just choose a basis and then construct a product topology out of it?
So one of the proofs that we did last time is that this is in fact a basis for a topology. So you can grab something and say, is this collection of sets a basis for a topology? That's something you prove, and it has to have two properties for that to be the case.
Right.
So we proved that this was in fact a basis, and that the thing it generates is a topology. So it's one of those things that we called it that before we proved it was the case. We proved it was the case after introducing the definition last time. Any other questions? Because I'm going to erase that and do the next proof. Okay, so now this next proof, we are working with, 7 different topologies. It's a really easy proof, I think. We'll see if I get stuck. But the hard part of it, of understanding it, is we're working with 7 different topologies. So let me write out all the different topologies, then read this thing, then explain what it is we're trying to prove. So let's see. We are going to have the topology X together with tau sub X. We're going to have Y together with tau sub Y. And then we're going to have X cross Y together with tau sub XY. And then these are exactly what you think. That's the product topology on these two things. Now I'm going to take a subset of A and give it the subspace topology. So from A here, so these two, we were crossing those together, which equals that. Here, we're taking subspace topology, so we're getting A together with the topology on A as a subspace of that product space. We're going to take a subspace topology here, and we're going to call this B together with tau sub B. We're going to take their cross product, and that is going to equal a topology on A cross B, and we're going to call that topology, is that tau 1 or tau 2? Let's see.
Tau 1, right?
That be the no, this is going to be tau 2.
Oh.
So this one's tau 2. Where you take these two subspaces and take their product together. So another one we're going to define is from here we're going to create a subspace topology on A cross B. And this one's going to be tau 1. So tau 1 is the subspace topology we get from here. Tau 2 is the cross product topology, is a product topology from these two subspace topologies. We're proving that tau 1 and tau 2 are in fact equal.
Okay, yeah.
So those are our 7 topologies.
That's better.
Okay, so I need to show that tau 1 is a subset of tau 2 and tau 2 is a subset of tau 1. And that's how we're going to prove it. So starting right here, I think that picture is going to be helpful in helping us think about things. So, let's actually read the proof now before we go on to prove it. So that we're for sure all on the same page. Hopefully this picture makes what we're saying here make perfect sense. So let X cross Y together with tau sub XY be the product topology on X with the topology on X and Y with the topology on Y. And let A with its topology and B with its topology be subspace topologies on X and Y. And let A cross B with tau 1 be a subspace of X cross Y with tau of X cross Y. So A cross B with tau sub 1 is the subspace topology of X cross Y with its. So this is a subspace one. And let A cross B with tau 2 be the product topology on A and B. So tau 2 is the one we get by multiplying those together. Then tau sub 1 is equal to tau sub 2. That's what we're proving. Okay, so let's do this. So I'm grabbing something from here. So I'll let V in tau sub 1. If V is open in a subspace topology, what do we know about it? It means that V is equal to U intersected with A cross B, where U is open in here. What does it mean to be open in the subspace topology? It means you're an open set in the initial topology intersected with the subset. So this is our subset, and so we have an open set intersected with our subset is what it meant to be an open set in our subspace topology. With me? Okay, now since U is open up here, then U is a cross product of two open sets. Right?
Yep.
So that gives me that there must exist U sub X in tau sub X, and maybe I'll just comma separate it. U sub X in tau sub X, U sub Y in tau sub Y, such that U is equal to U sub X crossed U sub Y. Right?
Yep.
So then we get V is equal to U sub X cross U sub Y intersected with A cross B. Just replacing U with U sub X cross U sub Y.
Okay, yeah.
Okay, so then notice what we said here. The cross product of the intersection of cross products is the same thing as a cross product of intersections. So this is the same thing as U sub X intersected with A crossed with U sub X intersected with B. Now notice that this is an open set on X intersected with A. That's what it means to be in tau sub A. This is an open set in tau sub A. This is an open set in tau sub B. And so this cross this is an open set in tau 2. So that gives me that this is in tau 2. Now we gotta prove the other direction. We gotta show that if V's in tau 2, then it's also in tau 1. But it's the same logic here. If V's in tau 2, what does that mean? It means that it can be represented as an open set in X intersected with A, and an open, sorry, that's U sub Y. And an open set in Y intersected with B. But then using what we showed up there, that's the same thing as that. So V is equal to now an open set in X cross Y intersected with A cross B, which is exactly what it means to be in tau sub 1. Follow that?
Yep.
Now we almost proved it. I actually cheated. And the cheat was what I warned you about at the start of class. Just because U is open in a product topology does not mean that it can be represented as a cross product of two open sets. Imagine our U was this blue together with the pink.
Yeah.
That's open. So really what we showed is that if V is in the basis for topology 1, then it's in tau 2. So all the basis elements from here are in tau 2, and then similarly, all the basis elements from tau 2 are in tau 1. And so we actually just showed that the basis elements from the first belong to the second, but that's saying the same thing. If I'm a topology and you're a topology, and you have all my basis elements, then you have all my open sets, because all my open sets are generated from basis elements. So if you have all my basis elements, you for sure have all my open sets. And if I have all your basis elements, I for sure have all your open sets. And so that's really what we proved. I just didn't want to confuse you with that detail at the start.
Yeah, makes sense.
But we did prove it. Okay. So that's the proof of Theorem 3.9. And now, let's do this last proof. We know that if you take open sets and you take their cross product, it's open in the product topology. What if you take closed sets and take their cross product? Is it still closed in the product topology? Pictorially, we sure hope so, right? If you take a closed interval, cross it with a closed interval, it gives you a closed interval, or it gives you a closed square, which we expect to be closed. So pictorially, we sure hope so. Let's actually check this and make sure it's the case. So, let's see, I'm trying to show that C cross D is closed in X cross Y. So I don't even know if I read this. Sorry, let me actually read it. Let C be closed in our topology on X, and D be closed in our topology on Y. Then C cross D is closed in our topology on X cross Y. That's what we're trying to prove. So I'm trying to prove that C cross D is closed. How do I prove that C cross D is closed?
Its complement is open.
Its complement is open. So let's look at its complement. What is the complement of C cross D? It's everything that's not in C cross D. So we're looking at X cross Y minus C cross D. I'm trying to show that this set is open. Right? Okay. So maybe this is best done manipulating it as we go. So let's maybe with my x's and y's, we get confused if I do a little point A, X, Y. I'm going to do A, B just so in case I accidentally write an x too small. It's not confusing. So I'm going to take A, B in this set. We're doing x minus y crossed with,
That's not quite right.
thank you, x cross y minus C cross D. This is what we're looking at, right?
Right.
And we're trying to show that that set is open. What is this set? What does it mean for a point to be in that set? It means that A is in X and B is in Y and not, parenthesis, A is in C and Y is in D. Breaking this down to the actual propositional logic that we use to construct sets. Let's look at the logic of this actual thing. Because I'm ultimately trying to rearrange this thing so that you can see it's an open set. Okay, so a point being in this set is logically equivalent to saying A is in X and B is in Y, and it's not the case that A is in C and Y is in D. Now I'm going to distribute a not over a conjunction. How do you distribute a not over an and?
You change it more.
You switch it to an or, exactly. So this is the same thing as A is in X and B is in Y, and we're distributing that not through. So it's going to be A is not in C, or, I did a Y there, B, or B is not in D. Still logically equivalent, right? Okay, now I'm just going to distribute these ands over that or.
Okay.
Maybe put this into words really quick. If I know that you're wearing a blazer and you're wearing a tie and you ordered the soup or the salad. I'm not, you're wearing a blazer and a tie and you ordered the soup, or you're wearing a blazer, you're wearing a tie, and you ordered the salad. So distributing an and over an or, you just apply to everything to both of them. You can show that with the table, but I don't want to take the time to make a truth table right now. So this is going to be the same thing as A is in X and B is in, I'm going to group my A's together. So I'm doing this, this, and this, or this, this, and this. And I'm going to group my A terms together just because they're both about the A. So A is in X and A is not in C, and B is in Y. So there's all our ands, and then we're going to or that with the next one. So group my A's together. A is in X and B is in Y, and B is not in D. Okay, so that's what we have, right? What does it mean for A to be in X and A to not be in C? That means A is in X minus C, right?
Right. The complement of C.
The complement of C, exactly. So I know A is in X minus C and B is in Y. Or A is in X and B is in Y minus D. Right? Okay. Now, A is in X minus C and B is in Y. That's the same thing as AB is in X minus C cross Y. A is in X minus C and B is in Y.
Okay.
Same thing as this, and or, sorry, keep the square bracket since I need to do the parentheses for my ordered pair. AB is in X cross Y minus D. Follow that? If AB is in X cross Y minus D, that means A is in X and B is in Y minus D.
Oh, okay.
That's exactly what it means when we say it's in the cross product of two sets. When I said that a point was right here, what does that mean? If I said this point right here, this point XY, so that point right there is a point X comma Y, what does that mean? That means its X was in A1 and its Y was in B1. That's what I meant to say X cross Y is a point in their cross product.
Okay.
Okay, so we're good here. So now I have an element is in this set, or an element is in this set. How do you or sets together? It's a union. Intersection is anding them together. Unioning them is oring them together. That means that AB is in this set union this set. So it's in X minus C cross Y union X cross Y minus D. Okay, so all that was just rewriting this set. This set is the same thing as this set, right?
Okay. That's cool.
All right. I know C is closed in X, so X minus C is open. Is Y open? Is Y open in Y? Yeah, the whole set is always open. Remember, for it to be in topology, you have to have the empty set and the whole set guaranteed. So Y is always an open set. So we have an open set crossed with an open set, which is open in our product topology. Similarly, we have an open set crossed with an open set, which is open in our product topology. Therefore, the complement of C cross D is an open set.
That's cool.
So I won't bother putting much words to that. Did enough explaining as we drew the picture out.
That's cool.
So that was tediously showing you all the logic of it. Okay. Any other questions on that? Nothing?
Yeah.
So our first assumption was that closed sets, or cross product of closed sets, gives you a closed set.
Yeah, that was our hope.
And it turns out that's not the case.
Turns out it is the case. Then C cross D is closed in X cross Y.
Oh, I misunderstood.
C cross D is closed because we just showed its complement is open.
Yep.
This is the same thing as this. This is an open set crossed with an open set, so that's open. This is an open set crossed with an open set, so that's open. So we have a union of open sets. A union of open sets is open.
Yep, I forgot we did the complement.
Yeah, so we were manipulating the complement the whole time. And so it works exactly as you would have hoped it works. And it better work because we would want to be able to create the topology on R2 from two cross product topologies on R1. From the cross product of two R1 topologies.
Yeah.
Alright. Nothing else with that? We're ready to talk about now about quotient topologies. Probably the most important of the three, if we're going to rank them by importance. And this will also be the easiest section in the chapter. We're only going to prove one thing, and it's that a quotient topology is in fact a quotient topology. The rest of this is just going to be a bunch of feel-good examples. Here we're really trying to develop a lot of just your intuition for topology from pictorial stuff.
Why don't we prove more stuff in this book?
In this part, we're trying to give you, this next section is heavily focused on developing your intuition from pictures.
Okay.
That's just the focus of the section. Next chapter, we start on continuous sets, or continuous functions, which is now the heart of topology.
Oh, awesome.
Okay, but anyways, so quotient topologies, what are we going to be doing? We're going to be gluing topological spaces together to create new topologies. That's how we think about it. Gluing them together, somehow sticking them together. Let me give you intuition for how that's going to work. So here I have, remember what I is. It's a closed interval from 0 to 1.
It is.
Yeah, that's what we use I for in this class. And we use S1 like this for a circle. We use T for a torus.
Yeah, that's right.
And we'll get used to some other things as we go.
Okay.
So here we have I cross I. So we're talking about this thing solidly filled in. Not just the boundary here. So solidly filled in like a piece of paper. And what a quotient topology is going to enable us to do is it's going to give us a way, here's how we're going to mark it. I'm going to construct the torus now from I cross I. I'm going to go from this to this, and I'm going to show you how. So here's pictorially how we say it. First, what I'm going to do is I'm going to identify this side with this side. So here's I cross I. When I say I'm going to identify these two sides together, that means I'm going to touch them together so that those endpoints are actually now the exact same point.
Oh, weird. Okay.
So when I identify those points like that, topologically speaking, here's what I have. Topologically speaking, what is this?
So,
It's not a cylinder. I don't know if we talked about a cylinder yet, but a cylinder would be I crossed R, all the real numbers. So topologically speaking, the cylinder goes on forever, and we'll use a cylinder for that. There's a reason we don't call this a cylinder. It's one that we've already talked about. It's a topology we've already given it a name to. Imagine what would happen if I kind of remember that intuitively what is topology? It's like rubber sheet geometry. As long as you don't rip things and glue things together, it's still the same thing, topologically speaking. You can stretch things out. So imagine if this paper now were made of really stretchy rubber. I had it stuck together like that. What would happen if I kind of stretched out the bottom here and flattened the whole thing out? What shape would I be left with? I'm going to flatten it. I'm going to stretch the bottom out so it's really stretched.
circle.
Kind of. We're going to have a hole in the middle still, right?
Oh, it's a torus, or is it our shape?
Not a torus. It's going to be flat, two-dimensional. It's just going to be an annulus, like a washer.
I don't remember that one.
Ring.
The annulus?
I don't
Oh,
remember that term.
well, you weren't in class last week then.
Ah.
It's one that we talked about last week. The annulus. It's going to be like a washer, like this,
Over there.
with these points filled in, out here. So it's dense like that, right? You see pictorially, you see intuitively how we would get that?
Yeah.
Flattening it up. So this, topologically speaking, is the annulus.
Okay.
Not a cylinder. Very different from a cylinder.
Yes.
I don't understand how a cylinder and annuals are different in topology if they can literally come from the same shape.
The cylinder goes on forever. It's R cross I.
Oh.
R being the real number line.
And I just an interval from 0 to 1.
And I is just an interval from 0 to 1. Now it doesn't matter if it's a closed interval from 0 to 1 or from 0 to 2000. Because in topology you can stretch it and it doesn't change it topologically speaking.
That's so trippy.
So is that just an arbitrary?
It's a consequence of the topology. We don't know what it means for two topologies to be the same yet.
Wow.
Here's what it's going to mean for two topologies to be homeomorphic. That's the word we use for the same. It's going to mean that you can create a bijective continuous function from one to the other and the other to the one. That's what it's going to mean. Okay, well, we don't know what continuity is yet. So, like I said, this section is meant to give you a bunch of intuition stuff to help you feel better about it when we actually get down to the dense definition stuff.
Okay.
So, this is all just feel good stuff. So, this is just to develop your intuition. Think about we can stretch stuff as long as we're not actually ripping. If I took this and I ripped it open, now it's something fundamentally different.
Yep.
And if I glue those together, now it's something fundamentally different. I had this, I glued those edges together, which gave me, not that yet, but just an annulus so far.
Okay.
Now I can't do it because this isn't all stretchy in a topology, but now imagine that I could grab this end and stretch it around and glue it back onto this end.
The torus.
Then we're left with the torus. So I could take this end here and identify it with this end. And then we have the torus. And so today what we're going to be talking about, we're going to be talking about quotient maps. Quotient maps are doing this type of thing. They're gluing things together like this. That to that.
Okay.
You start with I cross I, you run it through a quotient map, and this is what spits out. And you see how this topology results from doing some gluing on this topology.
Sounds like a function.
It
Is that a function?
It's going to be a function that maps it, yes.
Ah, okay.
We call it a quotient map.
Yep.
We use the word map for functions that go from a set to a set.
Yep.
So yeah, just running it through a function.
Okay.
Okay. Another thing that is going to help your intuition for this section is going to think about, it's going to seem like it's completely unrelated. You'll see how it's related here in a second. It's going to think about how we partition up things, create a partition on things, grouping them together. So you think about in your morning classes when you go to school, your first morning class, the whole student body is partitioned up into separate classes. And so you have everyone who's in, I don't know what you guys are taking, like physical science or algebra 2 or whatever. Each student shows up in one and only one class. And if I were to union up all the classes, I get back all the students. So the classes partition up the students. That's one partition. Here's one that's going to be pretty useful for us to think about. It's going to be how we partition up time into hours. How we partition up time into hours. What hour is it right now? 7. That's the hour we associate to right now.
Yep.
And we keep associating that until we get to 8. And then it's 8 onwards. So here we are at the very start of the day. Right? 0 here is meant to represent midnight of New Year's Day of the start of the year. Here it is. That first hour, what do we associate with it?
1.
Not 1, 12.
Wow.
The day starts at midnight, right? So we're going to assign all these points into the partition that we call the 12 partition. And then the next one is going to be 1. And then the next one is going to be 2. And then 3. And then 4. And then 5. And then 6. ... Notice that somewhere down here, 7, 8, 9, 10, 11, 12. Right around when we start lunchtime, we're going to get another one that we then assign to 12 again. And I mark the end of the day here, and then the start of the next day, again, we take that interval, and we're going to assign it to 12 again. And so we can take all of time, and we can assign it into these 12 sets, partition it up into, you're a 1 o'clock set, you're a 2 o'clock set, you're a 3 o'clock set. And we're partitioning up time into all these different sets. You're very used to doing this. So we're taking an infinite set of points, if we think about infinite number of sets of instances of time, and mapping it to just 12 sets. The 1 o'clock set, the 2 o'clock set, the 3 o'clock set, 4, 5, 6, 7, 8, 9, 10, 11, 12. Partitioning up time. So there's an example of partitioning something up that you're very used to doing on a daily basis. Okay. We'll see how thinking about that helps us think more down the line. So those are two examples to motivate the section. Now let's jump into the actual section material. So let X tau be a topological space, and let A be any set. A is not a subset of X. Maybe it's a subset of X. Maybe it's not a subset of X. It's any set.
Okay.
So we have X with a topological space and some other set A. For our example up here, we had X was all of time, and A is just a set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay?
Okay.
All right. So I told you this notation comes up a billion times, and you got to get very comfortable with this notation. Let P be a function from X to A. What does it mean for P to be a function from X to A?
Every element in X leads to some element in A.
Exactly. Every element in X is mapped to some element in A. Do we have to use up all of A?
No.
No. Do we have to use up all of X?
Yes.
Yes. We have to map everything in X to something in A. Maybe we mapped all the elements in A, maybe we don't. But we for sure mapped everything in X to something in A. Perfect. So let P be a map, a function. I'm going to often call it a map function, same thing. We just usually use the word map when we know the sets the function's going from and to, when we have them specifically named. So you can use those interchangeably. So let P be a map from X to A, or let P as a function from X to A be surjective, which means onto. So now we know it uses up all of A. Okay, so we got P is a map from X to A that's also onto. We define V as a subset of A. So remember, A so far is just a set. X has a topology, A is just some set. It does not have any topology right now. We define V as a subset of A to be open in A. So now we're giving it a topology. We define V as a subset of A to be open in A if and only if the pre-image of V is open in X. If the pre-image of the set is in tau, remember tau is a topology on X.
So is the pre-image just the input? Is the pre-image just X? Because I'm not familiar with that term.
Okay. The image, let's go down to this picture. Talk about image and pre-image. So here's X, here's A. Here's a point in X, here's a point in Y. Or sorry, here's a point in big X, here's a point in A. P maps X to Y. The way we write that out is exactly what you're used to. That means that P of X is equal to Y. So Y is the image of X is how we say that. And then P inverse of X, or of Y, is equal to X. X is the pre-image of Y.
Gotcha.
Now, let's just do something very clear here. I could also have Z down here, and I could also have Z maps to Y as well. There's no reason two elements can't map to the same thing. So in this case, P of X is equal to Y, but the pre-image of Y is equal to both X and Z.
Yeah, makes sense.
So the pre-image is everything that maps to it. So here we have some set in X that we're going to call U. And we run it through our function, and it spits out V over here in A. So if running U through our function spits out V, then we have to be kind of careful how we say that. I'm about to make some very dangerous assumptions. Just because the image of U is equal to V does not mean that the pre-image of V is equal to U. That's what I need to be careful about. Don't say that, because that would be a lie. Let's put back up what I had written here and understand why it's false for a second. But first, let's say exactly what it is. We run u through this function, and we get v. I don't know. We're still fine. We're fine. We're fine. Okay. So here's u in x. Here's v in a. If you run u through p, you get v. So we look at the pre-image of v. That's over here. That's u. If u is open in x, we're going to call v open in a. If the pre-image of u happened not to be an open set, then we would not call v an open set name. So v is open in a if and only if its pre-image is open in x.
Okay.
So define v as a subset of a to be open in a if and only if the pre-image of v is open in x. The pre-image of v is in our topology on x.
Gotcha.
Or in other words, u is in our topology on x. The resulting topology on A is called the quotient topology induced by P. Notice that once I have a set X and once I have a set A, there's tons of P's I could use to create topologies. So a different quotient map can produce a different topology.
Okay.
So this is the quotient topology induced by P. You have a particular map, it induces a particular topology. And we call P the quotient map. Okay, so P is the quotient map. Over here we have our quotient topology. Over here we had our initial topology. We have an initial topology. We pick a P that satisfies these two conditions. P is a function from x to a, and it's on 2. Then we can define a topology over here using that map. How do we define a topology over here? Well, we call the sets here open if, when you run it backwards through the function, the thing it came from was open.
And that just works.
Well, we're going to prove that this, in fact, gives us a topology. This is going to be the only proof that we do in this section. Now, before we do that, we're going to just run through a bunch of examples, try and establish intuition as much as we can before we just tackle the proof. It's not a hard proof. I just want to have all the intuition so that you can see how it's kind of obvious from the proof. Okay. So, let's do some examples. So, example. So we have R with the standard topology. What's the standard topology on R?
It's all of the unions of open intervals.
Open intervals and a union of open intervals. Perfect. So P is going to be a function from R to the set ABC, where R has the standard topology. Here's what our function is going to be. It's going to map, pick any x you want, pi, 1/2, 0.0001, 10,057. It's going to take any x, and it's going to map it to A if x is less than 0. It's going to map it to B if x is exactly 0. And it's going to map it to C if x is greater than 0.
Okay.
Make sense?
Okay.
So, pictorially, what does this do? This takes all the elements over here and this way, and it maps all those to A. It takes just this thing, and it maps it to B, and then it takes all the points over here, and it maps those to C. Okay, question. What is our topology then going to be on this thing? This is our A. A is equal to that. That's our A. So we have P is a function from some topological space to a set. How do we know what is open on A? We check its pre-image and see if that's open down here on R with the standard topology.
Which it is, right?
Well, what is? We need to write out the sets.
Okay.
Which of these sets are going to be open?
Which of what sets?
We're creating a topology on A. So what's a topology? It's a collection of subsets of that thing satisfying the 3 properties. What's the first thing that a topology has to satisfy?
It has to have the empty set and the entire set.
Has to have the empty set and the entire set. Okay, let's look at the pre-image of the empty set. What mapped to nothing? What real numbers map to nothing?
No real numbers.
These ones did. The empty set. So the pre-image of the empty set is the empty set. Is the empty set open?
Yes.
Okay, so the pre-image of this thing, which is acting, is open.
Okay.
So the pre-image of the empty set was equal to the empty set.
Okay.
So we're good. Okay, what else is in there? You said the whole set A has to be in there.
Yes.
Let's check that. Let's look at the pre-image of A. What is the pre-image of A?
All the numbers plus the
We want all the numbers, no, of the big A, of this thing,
Oh.
of this set, not of little a.
Everything.
So let's see. A is everything that mapped to little a or little b or little c. Well, all that mapped to little a, that mapped to little b, that mapped to little c. So the pre-image of A is all of R,
Yep. Which is open in R, right? Yeah.
which is an open set in R.
Yeah.
So A is open in our new topology.
Gotcha.
Okay, are there any other open sets? What about just a set containing A? What's its pre-image?
All the numbers less than 0.
So if we look at the pre-image of the set containing A, sometimes if it's a singleton set, we just write it as a single element.
Okay.
So the pre-image of the set containing A, or the pre-image of A, same thing in this context. That is going to be all the numbers from negative infinity to 0,
Not including 0.
not including 0. So that's negative infinity to 0. Is this an open set in the standard topology on R?
Yep.
Then that's an open set in A.
Yep.
Alright, what about just B?
Yep.
What's the pre-image of B?
Well, that's just 0.
Oh, sorry, little b.
That's,
Little b is just the set containing 0.
That's
Is that an open set in the standard topology on R?
no.
The set contains just 0. Is that an open interval?
No.
No. Can we get that from unioning up open intervals?
No.
No. Every open interval has infinite elements.
Right.
And if I union those up, I end up with a set with infinite elements.
Yeah, right.
All the topologies in this, all the open sets in the standard topology on R are infinite, except the empty set. Okay, so the set 0 by itself, definitely not. So the set 0 down here, nope. It's not in our topology. The set B down here, sorry. Because its pre-image is the set containing 0, which was not open in the standard topology on R. Okay, what about the set containing C? Is that going to be here?
100%.
100%. What's the pre-image of C?
All numbers greater than 0.
All the numbers from 0 to infinity. Is this open in R?
Yep.
Then, perfect. Then C is open in our new topology. What's its pre-image? It's right there. Is that open? Yep. So this is open.
Yep.
Okay. Let's see. What about A, C together?
Yep.
What is that going to be? That's going to be negative infinity to 0,
Union.
union together with 0 to infinity. Is this open in R?
Yep.
Then this is open
And A.
in A. And notice that, in fact, A is a topology. Did we get the empty set?
Yep.
Sorry, not A is a topology, but the C we generated is a topology on A. Did we get the empty set? Yes. Did we get A? Yes. Now notice that any union of those sets is also in there, and any intersection of those sets is also in there. Intersect those two, that's right there. Union those two, that's right there. Intersect those two, that's right there. Union those two, that's right there. So it, in fact, in this case, happened to give us a topology. Okay, maybe that's a crazy coincidence. Let's try another one. So we're going to do a quotient map again from the standard topology on R to the integers.
Okay.
So my x is R, and my topology is the standard topology on R. Okay. And our map is going to map to the integers, and we're going to map by what I have written here. First off, P of x is going to map straight to itself if x happens to be an even integer.
Okay.
So, in other words, negative 4 gets mapped to negative 4. Negative 2 gets mapped to negative 2. 0 gets mapped to 0. 2 gets mapped to 2. 4 gets mapped to 4. Okay, so we've taken care of those points. Otherwise, we map to n if n is odd and x is in the interval from n minus 1 to n plus 1. Maybe it would have been better if I wrote that the other way. We map to n if x is in the interval from n minus 1 to n plus 1, where n is odd. Okay. So now let's look at this. P of x. Let's look at minus, well, let's keep it simple for a second. Let's look at minus 1/2.
Okay.
Minus 1/2. So that is in the n. That's going to map to the n that x is within 1 unit of, where n is an odd. So if x is right here, what is the odd integer it's within 1 unit of? -1. So it's going to map to -1.
Oh, I see. Okay.
And this is going to map to -1. And this is going to map to -1. And this is going to map to -1.
Okay.
And so this whole section here, maybe do these in blue so it's a little easier to see from a distance. This, that's bad blue. This whole section here is going to map to -1. Once I get to -2, well, that maps to -2. Once I get just past -2,
Is there 3?
then it's going to map to -3.
Yep.
And so we're going to have this whole section here is going to map to -3. We're going to have this whole section here is going to map to 1. This whole section here is going to map to 3. Okay, so that's what our mapping does. Question: is this mapping surjective? Do we eventually map to every integer? Is there any integer we don't map to?
No.
Okay, so we used up all of the integers.
Yep.
So it is surjective, and it is a map from R to Z. That means it should induce a quotient topology. If we already had topology defined on R, we should be able to use P to define the topology on Z. So let's see what our topology would be. Rather than writing it out, I'm just going to ask you if some of these sets are open or closed. So let's look at 5. Open, closed, or neither? Let's do 4 first.
Oh, okay.
What's the pre-image of 4?
4.
Just 4. The set containing 4.
Yep.
Is the set containing 4 open in the standard topology?
Yes.
Is the set containing just 4 open in the standard topology?
No, I'm retarded. That's not.
No, it's not a union of open intervals. It's just 4.
Yeah, right.
So the pre-image of 4 is just 4, and 4 is not open.
Okay.
So this set is not open in the integers.
Yes. Right.
Is it closed? Well, we didn't prove. Maybe we shouldn't ask closed yet. Because we didn't say anything about if its pre-image is closed and it's closed. So we'll leave that off for now. We're just asking if they're open. Okay, so this one is not open. What about 5 now? What's the pre-image of 5 going to be?
It's going to be the interval from 4 to 6.
It's going to be the interval from 4 to 6, not including 4 to 6. Is this open in R?
Yes.
Yeah. So the set containing just 5 is open in our new topology on Z.
Okay.
Okay. Let's look at the pre-image of 3, 4, 5.
Yeah. Yep.
What's the pre-image of 3, 4, 5?
It's the interval from 2 to 6.
It's the interval from 2 to 6.
Included.
The pre-image of 3 gives us all that. The pre-image of 4 gives us that one point. The pre-image of 5 gives us all that.
Yep.
And so we're left with all the numbers from 2 to 6. Maybe using 2 to 6 was dumb. Maybe using 3, 4, 5 was dumb. Let's do -1, 0, 1. -1, 0, 1. Sorry, that's a bad one. Forget, I threw my bad one this one. Okay, so the pre-image of -1, 0, 1. What's the pre-image of -1?
-2, 0.
-2 to 0, not including 2 or 0.
Yep.
So the pre-image of -1 was negative 2 to 0. What was the preimage of 0?
0.
Just 0. And then, what was the preimage of 1?
0
0
to 2.
to 2. Union all those up. Negative 2 to 0, union was 0, union was 0 to 2. What are you left with? You're left with all the points from negative 2 to 2.
Yep.
That's an open interval. So this is open in the standard topology on R. So negative 1, 0, 1 is open in our new topology that we're defining on the integers. All right, let's try 4, 5, 6.
Yep.
What's its preimage? What's the preimage of 4?
3, 2, 5.
What's the preimage of 4?
Oh, it's even. Right?
It's just 4. What's the preimage of 5?
46.
Everything between 4 and 6. What's the preimage of 6? Just 6. So the preimage of this thing is a closed interval 4 to 6, which is definitely not open. Okay, so not that. All right, what about the empty set? What's the preimage of the empty set? The empty set. Is the empty set open in R?
Yes.
Then the empty set is open down here in our topology we're defining on Z.
Yeah.
What's the preimage of all the integers?
All the rails.
All the rails. Are all the rails open in R?
Yes.
Then all the integers are open in this topology we're defining on Z.
Yeah.
All right, starting to get some intuition for these?
Yep.
Okay. Now, just to know, let x tau have a topology defined on it. Let x tau be a topological space. And let x with this star up here be a partition on x.
Okay.
So x star is a set of subsets of x.
Okay.
If x was a student body, then x star might be something like taking the set of students in each class. So you'd have the set of everyone that's in algebra, and the set of everyone that's in biology, and the set of everyone that's in English. And then put all those together in a set, and that's our partition.
Okay.
Okay, so we have a topological space, and then we have a partition on X. We are typically interested in quotient maps that go from X to a partition on X.
Okay.
Those are the ones we're most interested in. All these other things, this was just to feel good about it. But typically, here's what we're interested in. X going to a partition on X. And so that's what we were talking about with time here. I used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But really, I meant this to be a set. Maybe I should have called it, you'd feel better about me calling this, I should have called this A1. Which were all the intervals of time that map to hour 1. And A2 and A3. ... all the way to A12. That probably would have been better labeling. Here, I'm mapping all these infinitely many points to that set, and these infinitely many points to that set, and these infinitely many points to that set. And so this is creating a partition on all of time. I'm dividing all of time up into 12 partitions. Each instant of time can either be found here or here or ... here. You just look at the clock. Oh, right now, this instant of time right now, it's in this set.
Yep.
An hour ago, that instant of time was in this set. So we are partitioning up all of time into these 12 sets. That's one example of a partition. Okay. Going to move the camera. Hopefully these are the two that write half decently. And we'll do some more examples. This time with partitions. Too far. Good enough. Okay, so let's go down now to another fairly concrete example. And then we'll do a completely discrete example. So here I have x. X is meant to be this interval, the black interval there. I'm going to partition it up into 5 sets. I'm going to take all the points here and put them in set A. All the points here, put them in set B. C, I'm going to put in its own set. I'm going to take that point and put it in its own set called C. So C is a set containing that point. It's not the point, it's the set containing the point.
Okay.
D gets all those points, E gets all those points. So that's how my P maps here.
Okay.
So P is mapping X to a partition on X. If I ran this point through P, it would spit out A.
Okay.
It would map it to A. If I ran this point through E, or through P, it would map it to E. Okay. So that's what P is. We're mapping X to a partition on X. Here's X star. It's the partition. It's the set of those sets. So writing it out explicitly, X star is A, comma B, comma C, comma D, comma E. And P maps from this set to this set. Maps all those points to A, all those points to B, that point to C, all those points to D, all those points to E. Cool. And notice that A is a subset of X. B is a subset of X. C is a subset of X. D is a subset of X. E is a subset of X. A partition is a collection of subsets.
Okay.
And notice that if I union A and B and C and D and E together, what do I get?
X.
X. That's one of the properties of it being a partition. If you union up all the parts in the partition, you get the whole set. Also, the other requirement for it to be a partition is no point can show up in two sets. Every point in X shows up in just one and only one of those sets. I can't have any overlap between A and B, in other words. Otherwise, I wouldn't be partitioning up my set.
Okay.
Okay. So, there's one example. Now let's do an extremely concrete example, where we actually label all the points, label our topology, just spell everything out. Very concrete example. So this time I'm going to let X be the set A, B, C, D, E. And the topology I'm going to give it, tau, is going to be this topology. We got the empty set in there, the set just containing A, containing AB, containing ABC, containing ABCD, and the whole set X.
Okay. Yep.
Now I'm going to let A be the set containing AB, and B be the set containing C, D, E. So my partition is AB, where A has those two elements, and B has those three elements. Notice A is a subset of X, B is a subset of X. Our partition is a collection of subsets of X. Those are disjoint, and their union gives me back X. So they're a partition of X. Okay. Drawing it out very pictorially here. In blue, I'm drawing what are the open sets. Because sometimes just looking at all that, it's easier to consume an image than to consume it just in writing. Okay. So question, what are the open sets over here?
Partition.
What are my open sets on my partition? Remember, this is a quotient map from a topology to a set.
Okay.
So how do I know if something's open over here? Its pre-image is open.
Yeah, right.
So let's start checking. So our topology that P induces. First off, is the empty set in there?
Yeah.
Yes. What map to the empty set? The empty set. Okay, so we're good there. What about just A by itself? Is that in there? What's A? It's little a, little b.
Yes.
Yes.
Or in other words, those are the things that map to A. So little a, little b, is that an open set? Yes. So A by itself is an open set.
Okay. Yep.
What about B by itself?
Yep.
B came from CDE. Is CDE an open set?
Yeah.
No.
No.
Why not?
Here's each of my open sets. I have the set just containing A, the set containing AB, the set containing ABC, ABCD, ABCDE. The set just CDE is not one of those sets. Or if you want to look at actually spelled out, here's my topology spelled out. Here are all my open sets on X. That isn't one of them.
Interesting.
So these are all my open sets, or drawn in blue. These are all my open sets. This is not one of the things I drew out in blue. So it's not one of my open sets. So the pre-image of B, which is this, is not an open set. So the set containing B by itself is not in there. What about the set containing AB?
Yes.
Yeah, because X isn't.
Because the pre-image of that is just the entire set X.
Yeah. AB gives us AB, C, D, E. What's pre-image of all that?
X.
All of X. That's A, B, C, D, E.
Yep.
All of X. So yes, this is our topology. Or if we were to draw it out here, remember we can't draw the empty set, so we skip that one and it's assumed from our picture. But that's pictorially what it looks like. Probably still seems kind of weird. Now let's see how this ties into everything I was talking about in the very beginning of the class. I've got X here now. X is a closed interval 0 to 1. And we're going to give it the standard topology that we give it on R. So open intervals. Think about this as a subspace of R. So open intervals are going to be our open sets. Now, what am I going to use for my partition, X star here? What I'm going to do is I'm going to map everything in X. So here's our picture for X. I'm going to map everything in X to a partition just containing that point X itself.
Okay.
So that gets its own point. 1/2 right here. If this is 1/2, we're mapping that to the set that just contains 1/2. Same with 3/4. Everything in there we're just mapping to a singleton set just containing itself. With one exception. D is going to contain 0 and 1. So both 0 and 1 get mapped to D.
Okay.
So after our mapping, everything got mapped to its own point, except 0 and D got mapped to the same thing.
Okay.
So 0 and D are combined together into one element now.
You mean 0 and 1?
Oh, thank you. 0 and 1, we combine them together with D. And so our mapping just took this and mapped it to what happens when we map every point to itself, except we combine 0 and 1 together in D.
So you turn it into a circle?
Yeah, we just barely did the quotient map for converting I, the closed interval, to the circle.
That's awesome.
That's the quotient map. It's a pretty simple one. We map the endpoints together, map everything else to itself.
Well, that makes, yeah, that's actually so cool.
Yeah, pretty simple. Nothing too complex about it. But just getting intuition here. So that's tying it back full circle to what we were talking about at the start with gluing things together. Now we'll do more example gluing things together, but we put off this proof long enough, so let's do this proof, then do more feel-good examples, and we'll be done for the day.
Okay.
So now we need to prove that this topology induced by our quotient map is in fact a topology. We've been calling it a topology, we've been pretending it's a topology, it's happened to work for our examples, let's actually prove it. So, let X be a topological space, and let P be a map from X to A. Let P from X to A be a quotient map. So, it maps from X to A, and we know it's surjective, or onto. Okay. Then the quotient topology induced on A is in fact a topology. So we need to prove, maybe we'll just label that thing. So let tau sub A be the quotient topology. And we basically need to show that tau sub A is in fact a topology. That marker's dying. A work better, blue work better. Okay, 2. So first thing we need to show is that the empty set and all of A are in there. Right?
Yep.
So, since P is on 2, comma, then the pre-image of A has to equal all of X. Since it's a surjective map, since it's on 2, it maps everything in X to everything in A. We use up all of A. So the pre-image of all of A has to be all of X. Okay. So that gives us that A is in our topology. And we know that the pre-image of the empty set is just the empty set, which gives us that the empty set is in our topology. Okay, so there's the easy ones. Now, what do I need to do? What's the next thing we have to prove about topology?
So that the intersection of your finitely many if your open set, finitely many of your open sets and the intersection them together, that would be your topology.
Perfect. I need to grab a finite number of sets out of there. So tau sub A, this thing that we're claiming is a topology. I need to go in there and grab a finite number of things. Doesn't matter. 10, 100, 10,000, you choose. Doesn't matter. Any finite number n, I need to go grab that many of things out of there, intersect them all together, and make sure it gives me something that's also in there. Otherwise, it's not a topology. So, next we need to let v1, comma, v2, comma, dot, 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 comma, vn, all in tau sub A. What does it mean to be in tau sub A?
It means you're an open set in tau sub A.
Well, we're proving tau sub A is a topology, so that's not quite the case yet.
Oh, okay.
But if you're in tau sub A, how did we construct that tau sub A thing?
Oh, the pre-image. It's an open set in your pre-image.
Its pre-image is an open set.
Yep.
So let those in tau sub A, then I know that there must exist u1, comma, u2, comma, dot, 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 comma, u sub n in tau, in our initial topology up here. There must exist these things open in X such that u1 is equal to the pre-image of v1, comma, u2 is equal to the pre-image of v2, comma, dot, 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 comma, u sub n is equal to the pre-image of v sub n.
Wait, shouldn't it be, I feel like you got the u and the v switched. Because shouldn't the v be equal to the pre-image of, or am I thinking that wrong?
No, A is the set we're mapping to.
Yes,
So the V's are in A.
yes.
So they're the ones with the pre-image.
Oh, I see how that works, okay.
We're mapping from A to X.
Yeah, I see how that works.
Keeping this picture in mind.
Yeah.
That'll probably help keep things clear. Okay. So 4. Then, the pre-image of the intersection of, I'm trying to show that the intersection of all these things is also in tau sub A. Which means I need to show that the pre-image of the intersection of all these things is open in tau.
Yeah.
So that's why I'm writing out here. So let's look at the intersection from I equals 1 to n of all of our v sub i's.
Okay. That's a tau. Right.
We need to show that that's a tau.
Yeah.
Okay, so this is equal to, in fact, I probably didn't need to list out all this stuff. We could just skip straight to this. So I think all these middle lines are completely useless. And we might need the space. I don't know. So let those in tau sub A. Four. Then the pre-image of the intersection from I equals 1 to n of all those v sub i's is equal to, now here's where we have to do something going all the way back to Theorem 0.22 when we were doing the preliminary stuff. When we were doing that, we showed that the pre-image of an intersection is equal to the intersection of the pre-image.
We did?
All the way back to chapter 0, to our preliminary stuff. So in other words, you can factor an intersection out.
Yeah, right.
Okay, so in other words, we can factor that intersection out. If you can do it with 2, you can do it with finitely many. So this is the same thing as the intersection from I equals 1 to n of the pre-image of v sub I. Now, I know that the pre-image of v sub I is u sub I. Okay, we could call it u sub I. But u sub I is
in topology.
is in our topology tau here. So in other words, the preimage of V sub I is open
Yeah.
in tau. So a finite intersection
Must also be open.
must also be open.
Yep.
So this thing is in tau,
Okay.
which gives me that the intersection from I equals 1 to n of V sub I must be in tau sub A, because its preimage was in tau.
Yep. Makes sense.
Perfect. On to the next one. Now, let V sub alpha be any arbitrary collection of subsets of tau sub A. Take any subset of tau sub A that you want. Maybe we have infinitely many things out of tau sub A that we choose. Maybe we only choose one set. I don't know. Some arbitrary amount, but we're no longer limited to a finite amount. Then, the preimage of the union of all those sets is equal to the union of the preimage of all those sets. Maybe makes more sense to try like this. The preimage of union up the preimage of each of those sets. V sub alpha, each of them, grab them, union them all up.
Oh yeah. Yeah.
Okay. And let's see. Each of the preimages of those V sub alphas has to be an open set in tau. So this is an arbitrary union of open sets in tau. So it is in tau. Which gives me that the union of all those V sub alphas is in tau sub A. And we're done.
Yep.
So it is in fact a topology. We showed it has the empty set, we showed it has the whole set A, we showed that any finite number of sets out of there, then their intersection is also in there, and we showed that any arbitrary collection of sets out of there, their union's also in there.
Makes sense.
Okay, so let's now move on to more of this gluing. Again, just examples here. So you tell me what it is just from the picture. So what am I doing? My quotient map is going to take this square. All the points in the interior here are just going to get mapped to the set containing just that point.
Okay.
On the other hand, I'm going to map all the points here with all the points here. So that point and that point both are getting mapped to A. That point gets its own set B, this point gets its own set C, this point gets its own set D, but that point and that point are mapped to the same set. This point and this point are mapped to the same set. Corresponding points down these sides are mapped to the same set. And so when it's all said and done, what do we get?
Cylindrical but not a cylinder shape.
We get an annulus.
How is
Stretch it out and flatten it. We're going to force this to fit flattened out. Remember, think about it made of rubber that is infinitely stretchy. You can stretch as much as you want. It's impossible to rip this stuff.
Yeah, okay, that makes sense.
Okay, so I give us an annulus. All right, let's look at the next one here and see what that gives us. So I'm doing the same thing now. I'm mapping this side to this side, but I'm twisting it as I do it. I'm making these points map to those points. So that point is mapped with that point. Now what does that give us?
Kind of a spiral helix shape thing, I don't know.
Has a very famous name. You're on the tip of it. A Möbius strip. It's exactly, folding the paper might make it biased. It's exactly what's on the cover of our book here, a Möbius strip. And so what we're doing is trying to do this. It's being more difficult because it's folded paper, so it's not so thin. But so I am mapping this point right here with this point right here. Right?
Yes.
So when I do that mapping, I'm trying to force those 2 points together. Let me mark through all the way to the other side. A point doesn't have thickness, so it shows up on both ends of it. So lining up with the blue I have written there, that comes through right there, and lining up with the blue I have written here, that comes up somewhere like right here. Okay, so that's that point. Getting on both sides to be able to see it. Okay, so I've got to take this over and fold it around, but I can't just put it like that. Those 2 points have to be the same point, so I'm required to. This is much better if I would have cut paper beforehand rather than just folded it.
It works.
And that's what it gives us, this twisted thing. Now this twisted thing is a pretty interesting twisted thing for a lot of reasons. One reason it's interesting is how many sides does it have?
One.
It has one side. My finger's right here. I'm going to keep moving in a straight line. So I'm moving in a straight line. That takes me here. That takes me here. Moving in a straight line. Moving in a straight line. Moving in a straight line. Right here. Right there. Unfortunately, I'm going to have to move my hand. But we were right here. Moving in a straight line. We get back to where we started. If you were a two-dimensional being that lived in this universe, two-dimensional being moving along, if you started here and kept going straight long enough, you come back right where you started.
Yeah.
So that's one nice thing about it. Here's another nice thing about it. This is a two-dimensional thing. Notice that we have to use 3 dimensions of space to fit this thing. You can't somehow smash this down and write it in the whiteboard, because then you get all these things crossing. It just doesn't work anymore. So even though it's a two-dimensional object, the only way to represent it is in our 3 dimensions of space.
Because it would overlap, it would intersect and kind of.
Right, you can't just draw this thing two-dimensionally.
Right.
You can draw this two-dimensionally.
That's weird.
This one, when you had it like that annulus, you could flatten that out and draw that two-dimensionally. But the Möbius band, no way to do it.
Even if you stretched everything around, that's so weird.
You can't untwist it. There's no way to undo that twist anyway.
Called a
Man,
Möbius?
that's wild.
It's called a Möbius band, or a Möbius strip.
That's,
Very interesting.
I get it.
So this right here gives us a Möbius strip.
Okay.
Okay, let's look at this one. This one, I'm assigning those points with those points and those points with those points. So see if you can do this without me giving you the paper. Just try and picture what's happening here. I'm taking those, wrapping them around to touch, and then wrapping those around to touch.
You gotta give it a
Torus
rest.
center.
That's going to be the torus.
Torus.
Good. This is our torus.
Torus is cool.
Notice that the torus is a lot like what we had here.
Just you add them.
Right, so this was, we wrapped those around, and then the torus was, now wrap this end around back to this end.
Yeah.
So you can think about this as somehow being a cross-section of the torus. Right? If you had the torus, this would be like a piece that you could cut out of it.
Yeah.
That's what I mean by cross-section.
Oh, yeah.
And you see why I'm bothering to tell you that when you try and think about this one.
I don't even know.
This one is called the Klein bottle.
Oh, I know Klein model.
So the Klein bottle, let's start by associating this side with this side. That gives us a Möbius band. So I'm associating this side with this side, so I gotta do my twist as I go, right? Try and get the paper to kind of cooperate without me having to turn it. Okay, so that gives us that. But now I need to take, you can't really see the edges, can you? Let's see if we can,
Mark it.
yeah, color in this whole edge blue so that you can see it. Color it in on both sides, since but now, so I got the Möbius band. Like that. And now I somehow need to take the blue edge and wrap it around to connect on the white part.
I've seen a Klein bottle before, and if I understand correctly, the glass has to like go through the plane for it to be.
Right, we can't really make a Klein bottle in 3 dimensions of space.
Yeah.
And so they create 3D images of a Klein bottle that you can go get that are meant to represent it, but it has to intersect itself.
And that is possible, like that's legal in the system that we have.
So, the same way that you can't get a Möbius band in 2 dimensions, you can't get a Klein bottle in 3 dimensions. If you want to completely represent the Klein bottle, you need 4 dimensions of space for it.
Yeah, if you do it in 3D shape, you have to represent it.
And so you go look at a Klein bottle, you see the images that they have for a Klein bottle, you can look it up, look at the generations of it, it's really cool to watch. That object is an object that has no inside. Has no inside, it has no outside, the same way that the Möbius band has no inside or outside. You can think about this as a cross-section of the Klein bottle. And so if you're over here on the inside and you keep going long enough, you eventually are on the outside of the Klein bottle.
Yeah. But it's like in every direction.
That's strange. That's neat though.
In every 3 dimensions.
Yeah, that makes sense.
So, yeah, you need 4 dimensions to represent a Klein bottle properly.
So this just extends infinitely, I assume.
What?
You could just have an infinitely many number of these shapes, just increasing the dimension every time. So you have a Möbius strip, which is a 2-dimensional Klein bottle, and then you have a Klein bottle, and then you have a 4-dimensional.
A Möbius strip and a Klein bottle are still 2-dimensional objects. They're both surfaces.
Oh, okay. What?
But a Klein bottle is, because look at this. I mean, it's basically this square. If you existed in this universe, you could map your universe with the square like this. The same way that we use flat maps to map the Earth.
Yeah.
So your universe, you're still just in a 2-dimensional universe, a 2-dimensional being. But now it takes 4 dimensions of our space to represent, if you wanted to make a subspace topology on the Klein bottle, you would have to have it as a subspace of 4 dimensions of R.
That's so.
So trippy, so weird, but fairly easy to represent
Yeah.
with just a simple quotient space.
So
You might think, how on earth would you ever construct a topology on that? Turns out it's real easy. Although picturing the thing is a nightmare.
I get curious because if in a Klein bottle you can travel in all directions and there's only one side. That's so weird. But like, I think of also a circle. You can also travel in all directions on a sphere. But I guess that's not really. Is that the same thing? Because you're connecting. Oh.
It's not the same thing as a Klein bottle. A sphere has 2 sides.
It does have 2 sides. Okay.
A
so
Klein bottle has 1 side.
That's like the difference.
The inside of the sphere and the outside of the sphere.
If you start on the inside of the square, you
The same way that this has 2 sides. If I'm right here, I can never get to the other side.
Yep.
But if we make it a Möbius band, if I can, now it only has 1 side.
I'm blowing my mind.
Yeah, we're starting to get to where topology gets a little bit funner. It gets really fun with manifolds, but hey, this is fun too.
that sounds so fun.
Manifolds.
Yeah, manifolds. Okay, see if you can figure out what this one is. Here we have the disk, and we're associating all those points with all those points.
So you're folding it out. Right. Yeah. You're folding it out.
Real similar to the stuff we've already been doing up here. See if you can figure out what it is. You have to associate those with those. Remember, that's a disk that's solid filled in the same way that these were filled in squares. But your only points that are allowed to be touching are these points touching those points. I can't let this point touch that point.
Yeah. Right. So.
Be like one with this is.
Fold that.
Well, first I could shove in this part of it, like stretch it out, grab the rim and kind of pull it out. So it creates like a half sphere, right?
Okay.
And then finish folding the edges in on each other.
Wait, okay, so it just folds up like this, like a taco?
It gives you a sphere.
What?
And that's a sphere.
What?
That makes sense. No, it does make sense.
So you grab the circle part. Let's see if there's some way I can easily represent this. Oh, that's a whole chord. So imagine this is me grabbing the edge of that thing. I can pull that out and shove the in part in. So that stretches and gives me a half sphere easily, right? And then I just fold the rest up. Fold the rest up. That chord's not very bendable.
So a sphere, if let's say you just had a circle and you folded, or a flat piece of paper, and you fold it and sealed off the edges along the side into like a taco shape or half a circle, that's also equivalent to a circle?
It's
Or
equivalent
sphere?
to a sphere.
That's what I'm saying.
Yes. It's topologically equivalent to a sphere. Meaning, so these are the only ones touching. So you create a taco, but a taco where you're very careful that only the edge is actually touching. And then there's a little bit of space inside there.
Yeah, okay.
And then
Give that substance infinite stretchiness, you can stretch it out into a sphere.
Yep, okay, yeah, yeah.
And so, yeah, it would be topologically equivalent to a sphere.
Yep.
And you can look at, get on YouTube, look at images of some of these things being generated, how you show you these things. It's really cool to watch them come to life. And then finally, here's another one that's a tough one to think about. And that's a projective plane.
Just a Möbius sphere.
Kind of.
what are those arrows are exactly are they trying to communicate? What's the difference between up and down?
Okay. Let's make sure the arrows make perfect sense. Otherwise, these charts are pretty useless.
Like the double arrows.
So this right here, when I had the arrows both pointing in the same direction, that means that we keep the orientation of this and this the same. So that is folding like this. So this point gets folded to that point.
Yeah.
When I have the arrows opposite directions, that means you flip the orientation as you do it. So now that point has to touch this point. So that means I have to flip it as I go. Here's my edges. Here's A. I have to make these two meet up. And so that's requiring me to twist it. And so that's why this is the Möbius band, whereas this is just the annulus.
Yeah.
Good.
What about the
So
double
yeah,
arrows?
this, you can start by making a half circle, a half a sphere, but then when you go to close it, you gotta twist it.
I can't even picture that.
Well, yeah, that's because you need 4 dimensions of space in order to get that generated correctly.
Oh, no.
So it's going to be intersecting itself when it shouldn't be. The only way we can picture it is it intersecting itself when we view it in 3 dimensions of space. The same way you've seen images of a Klein bottle, they intersect themselves. They say, but pretend it didn't actually intersect itself. It went around into the 4th dimension and came back.
Well, alrighty then.
And this one's called the projected plane. I highly recommend going and looking at videos of the Klein bottle and the projected plane and seeing why this is called the projected plane. But it's nothing that you should all be able to guess from just looking at that.
What do the double arrows mean?
It just means this side's going to this side.
Oh, to label.
Just a label.
Yeah, just to label them differently.
I see.
Ooh, that's cool.
Okay, and then the last process we have is this process of, we call it the connected sums, but it's like adding topologies together rather than gluing them together. How does this adding process work? So I've got some topological space here, S1, and some topological space S2 here. The way it works is I am going to come over here and I'm going to cut out a patch of it. I'm going to come over here and cut out a patch of it. So now those are holes into the surface.
Yep.
And then I'm going to identify these points with these points.
Okay, yep, makes sense.
Glue them together. So it's basically first cut holes and then glue them together, rather than just gluing together. These were just gluing together. For the connected sum, you cut holes into each of your topologies, then stick them together.
Yeah,
And so the result looks like this.
okay.
So let's do it for a torus really quick, just to get a feel for this.
Okay.
So I'm going to do taking 2 toruses and adding them together. So when this is all said and done, it's going to give us S2. That's a donut, that's a donut. Let's represent these. The torus. So we have this. I don't know if the author, I think he might have just used numbers to specify which side goes to which side rather than having to count up all the arrows. So I'm just calling that side 1 and side 1, and then this goes to this, and we're just going to call that 2, 2. Rather than having to count the arrows because I have to draw another image over here.
Yeah.
Okay. And then over here, I have another torus. So call this 3, 3, 4, 4. Okay. Now I'm going to glue my two toruses together. So I got to cut a hole out of each of them and then hook them together. Pictorially, same thing we did right here. But now I just have two donuts on either side that I'm hooking together.
Okay.
Okay, so to cut it out, what we have to do, representing that would be something like this. Coming from this corner, I'm going to cut out here, this edge. This is 5. And I'm going to cut out this edge here. And this is also going to be 5 because I'm going to glue these two together after I cut out the hole. If we cut out the holes, this is cutting out the hole, so now it's just this part of the figure. This part's cut out. It's just this part of the figure, this part's cut out. And then we put the two holes together. And so this one's going to be oriented this way. Notice that those are opposite. That way when I fold them together, I can stick them together.
Yeah.
You'll see why I did that in a second. So I'm taking this one, I cut that corner so that corner's not a thing anymore. So I'm stretching this out. So I've got that 5 right here. Here's my 5 pointed down. And then I had my, I have my 2, my 1, my 2, my 1. So my 2, my 1, my 2, my 1, my 2. This is why I draw pictures before you guys come. Just keep driving nuts. Get it half decent. Okay, doesn't matter that much. All right, so this right here is going this way. This is my 2. This is going this way. This is my 1. This is going this way. This is my 2. And this is going this way, and this is my 1. So that is getting glued to that, that's getting glued to that.
Yep.
Representing this one over here, remember I cut that. So I'm going to turn it like that. So notice that that 5 is going to be pointing down when I flip it. Because I open it and turn like that.
Is an edge though? Can an edge really be pointing down?
We're stretching it out. Everything's stretchy here.
Uh-huh.
So I've cut in right here. So that's a little hole in now, right?
Yep.
So that isn't there. So first I'm straightening that. So pull it straight so that my 5's at the top.
Yeah.
My arrow would be pointing that way. Now turn it.
Okay.
So here's my 5 pointing down now. Hopefully that makes sense. And then we have my 3 here. This is this 3. My 4 here. This is this 4. My 3 here. And then my, let's see, my 4 is here, right?
Yep.
Okay, and now I'm gluing those two edges together.
What exactly do you mean by gluing? Like,
I am identifying this point with this point, this point with this point,
so you're making
this
them
point
the same.
with this point. I'm making them the same point. It's my quotient map. Gluing is quotient map. Hooking together is first cutting holes, then making your quotient map.
Ah, gotcha.
Cutting holes, then gluing. And then so when that's all said and done, obviously what I'm left with is just octagon.
Whoa.
We'll call this my 2. This is my 1. This is my 2. This is my 1. This is my 4. This is my 3. This is my 4. This is my 3. Now, hard to see it from that, but then if you would fold all those things together the way that it goes, you'd be left with this shape, S2.
Okay, I have a question that's completely based off of my intuition. But if you have a 16-sided polygon and you construct it like that, is that 3 toruses put together?
Highly unlikely.
Okay.
You kind of just did a big massive gouge out of for your 5, but it seems like that 5 could actually be as small as you want it to be.
Yeah, that's just so you can see it.
Interesting.
Remember, size does not matter in topology.
Yeah.
Doesn't matter how small we make those holes, how big we make those holes, stretching everything out. It's infinite stretchiness, and you can think about it somehow injecting infinite amount of mass as you stretch it, or sucking it out as you stretch it.
It's like a way to give yourself another edge.
It's what it would be to cut a hole in it.
Yeah. Well.
So it was me cutting a hole.
Yeah, right.
So that's pictorially how you would have to represent that. So I had two toruses that
Okay.
were separated to begin with.
Why couldn't you just like, I mean, so theoretically you could just cut it like a triangle, the tip off, theoretically, right?
I just need to puncture a little teeny hole in there. And then it completely changes the topology.
Oh, yeah, alright.
I pop a hole out, puncture it.
But just bear with me a second here. If you had your square and you just cut an angle off on an angle, one of the corners off, is it technically doing the exact same thing you did there, right?
Cutting off the corner.
Of your square.
Sure. Sure.
Yeah, I see what you're saying.
Just curious. I mean,
I think
just wanted to
so,
play
if
around.
I understand what you're saying.
Yeah, that makes sense.
Because you're just giving yourself another edge, is all I see you doing.
Yes, with what these edges represent. Remember, an edge ultimately represents something being folded to something. So an edge are the side points I identify with other points. So I'm intentionally reorienting this thing so all my edge points are the ones that get glued together in the process. So being on the edge means something special here.
And you just somehow created another one, and that's all that matters.
I cut a hole in it. This is pictorially cutting a hole.
I'm just saying, however you do it, it doesn't matter as long as you're creating another of these theoretical edges.
Yes.
Interesting.
Yeah, your hole ultimately should add one of those edges.
So is cutting a hole like removing a set from a topology?
Yes, it's removing some points from the set. Not removing a set from the topology, removing some points from your overall set.
Oh, from the set X?
From the set X.
Okay. Why? Wow, that seems like it shouldn't change as much as it does.
Intuitively, it puts an edge on it.
Well, yeah, pick
So I've got R2 here,
Uh-huh.
and then I get rid of this open set in R2. So now there's this hole here. If we draw the picture, there's now a hole in R2. Topologically speaking, that's a very different thing now.
Uh-huh. Right.
So that's what putting a hole in it is.
Makes sense.
If you put a hole in your Möbius band, then suddenly there's a place to go from one side to the other side.
So it's two-sided now.
Well,
Wait,
I'm not sure how to say that.
Wait, how does that even happen?
Well, it doesn't. That's why you make things really ugly unless you smoothly glue it into some other topology that just continues into.
I see. Yeah.
So it's a process that we go through. We don't just go around cutting holes and then leaving it, because that's a pretty ugly thing. We cut holes and then smoothly fuse those holes together,
Uh-huh.
like welding. Sure.
Yeah, that's pretty neat.
Anyways, so that's just a bunch of feel-good examples.
That's cool.
Next week we start the heart of topology. We start continuity and homeomorphisms.
That would be so cool.
That sounds like that.
Did you have any questions that you want recorded for this lecture?
Is there other ways to join two topologies that don't require, well, I shouldn't say they don't require cutting holes, but are there other ways like intuitive?
There's no way to connect those two things you have to do some sort of gluing process.
Uh-huh.
And if you don't cut the hole first, then kind of intuitively what you're doing is you're like having a double layered part on there.
Uh-huh.
And so they're not really,
Okay, couldn't you just take your
Huh?
two,
They're not really connected.
couldn't you take your two topologies, squish them together, and then just remove the intersection? Wouldn't that do the same thing?
I have to think carefully about that because, so let me give you something that would be really ugly to try and create topology on.
Okay.
This circle touching with this circle at a single point.
Okay.
That's something real ugly to create a topology on.
Nice.
Why?
We ultimately work our way, a lot of what topologies are working towards, I guess if you're getting into knots, I'm thinking about in terms of manifolds. You couldn't create a manifold on that thing.
Okay.
But yeah, it's not nicely behaved having these sudden sharp points in there.
It is like legal.
Huh?
It is legal.
There's no reason that we couldn't have this. There's no reason that we can't define a topology on that thing.
Okay.
It's just not a very nice one.
So that is a way to do it without a cut and hole, essentially.
Yeah, there's no reason that you can't just take those two things and glue them together. It's just not a very useful thing to do because the result is really ugly. What's much better to do is to cut a piece, cut those two, and then fuse their ends together. And then you got something that's really nice to work with. But you're right back to where you started in this case, which is back to circle.
It's true.
Yep.
What's my question now?
To give you a sense for kind of why these things are ugly, is because imagine that we're giving this a topology from R2. So most of our open sets would just be open intervals. That's open in R2, so how does that intersect? It's an open interval.
Yeah.
Look what happens when we intersect that thing.
Yeah.
All the open sets intersecting that thing, they're not open intervals anymore. They're ugly, and so we can't talk about the basis elements being these nice open intervals. So it makes our topologies ugly.
That's sad.
Whereas with these nice gluing togethers, from here to here, I can still think about open sets on this as being intersections with open three-dimensional balls. And now all my open sets are behaving just as nice as you always expect them to.
Yep.
So it's stopping something ugly happening. I know ugly is a bad word, but I don't know how better to say it. Something messy, something you don't want to work with, something that's not particularly useful. It's just ugly.
Yeah.
Okay. Sorry.
Go ahead.
Okay, I'll have a couple questions. One is I'm assuming that if it's not a complete closed set and there are some already holes in it, you could at any point merge them together without having the cutting process.
Most of the spaces we are interested in are in somehow
Fully closed set?
finished.
Doesn't that mean closed?
Not punctured. Closed means your complement is open, so
Finished and closed?
they're nice. It's easy to talk about the open sets on them.
Okay, but let me just get straight though, like the ones we were talking about were closed sets and you had to open up a side to connect them.
They were just surfaces. They're just surfaces.
So they're not, because
Oh, they're closed surface in that sense of the word. Okay. Yes.
now what's really,
This was a closed surface, but notice that this isn't a closed surface.
now what's really confusing to me, sorry, is, okay, if we're opening up a set, the edge is still closed, like around the hole that we made.
If we're opening up a set,
So if you're cutting the hole out of it, then the edges of the hole are closed, I think is what.
I just want to clarify that's the case.
the edges of the hole are closed. So when you cut out a hole, when you remove an open set, then what you're left with would have been considered a closed set in the initial topology.
Okay, so
Right.
we're always cutting out open sets.
Yes.
Got it.
Sorry.
Why don't we cut our close up? What's gonna happen?
Well, there'd be nothing to connect. It would always be one easy, like.
He's thinking about you miss your boundary points.
Yeah, there'd be no.
If you cut out a closed set, you'd cut out some of the boundary points, and it's the boundary points you naturally want to glue together.
But can we not glue in any of the non-boundary points?
If you take the set and remove the biggest subset you can that doesn't include the boundary points, you remove the interior, which is an open set.
Yeah.
So if you keep all the boundary points, if you're making the boundary of your cut your boundary points, you removed an open set.
Can we glue open sets that aren't boundary points, is what I'm trying to say?
When we do this gluing process, we always do it with boundary points.
But can we do it without boundary points?
I mean, you can do whatever you want. It's just not going to be nice.
Okay.
Like, there's no reason that you can't do this. It just is a real ugly topology.
Right.
Whereas this is preserving a bunch of those nice properties
Okay.
that the previous spaces already had.
Yeah, okay.
So it's more structure preserving. Maybe that's a good way to say it for now.
I see.
More structure preserving until we get further along. And
So you can technically glue any point inside of your interior to another point inside of a different subset's interior, essentially.
sorry, what?
You can glue an interior point to another interior point somewhere else.
Sure.
Okay. Cool.
Yeah, you can glue together whatever you want. You can create whatever map, whatever quotient map you want. Just has to be surjective.
Right. Okay.
Yeah.
Interesting.
Interesting.
It's just a matter of if your resulting topology is going to be very useful or not. And if you do these mappings right, your resulting topology, it turns out, will have a lot of the same nice structure that your previous one had. If you do them wrong, then you're getting up with a pretty useless topology, something that you can't really do anything with.
I see.
Anything else? Cool. We'll call it there and see you guys next week, I guess.
Thank you.
Hopefully we see you next week.
Yeah.